All right, good afternoon, everybody. Today we are going to do a little more implicit differentiation. We're going to start 2.7 related rates. Pretty much everything that's on the exam, which is on Thursday, we've already covered. So the stuff from today will not be included on the exam. I sent out the review last week. There were 2 reviews, actually 2 old tests or reviews or something like that. I think I had said in class I'm not intending on providing the solutions to those reviews, but if you had questions over anything, you could ask me. You have to just come to my office hours or text me or call me, and we can set up a Zoom meeting if you'd like to discuss something. So, are there any questions? Everyone feels okay about Thursday? Okay. I hope we'll have a little time maybe at the end of class to answer any questions you might have, but otherwise I'm going to get started if you don't have anything. Okay, let's do it. So implicit differentiation, let me just remind you what we did last time. So last week we said that if we have an implicit equation, that means an equation that we could not solve for x or y, that we could find dy dx using this thing called implicit differentiation, which really just meant that we would be taking the derivative on both sides of the equation with respect to x. That's really what the implicit differentiation meant. So it was like, okay, we were given some equation, the equation had a left side and a right side. And then all we would do is we would apply the derivative to both sides, in this case with respect to x, and then use whatever rules we needed, right? There could be product rule, there could be quotient rule, there could be chain rule, whatever we needed to do to take derivatives, we would do that. After we did the derivative, then we would normally try and just use algebra to solve for dy dx, right? So that's what the homework was about. Those problems are on the review. And that's what we did, right? So I want to talk about I want to do a problem with you, okay? And I give you an implicit equation, and then I'm asking for 4 different things, all right? So let's just start with the first one. All right, the first thing I want you to do is find dy dx. So when I write dy dx, what I mean by that excuse me, is if you look at the denominator has dx, right? That means that we are going to take the derivative with respect to, WRT, with respect to, is that okay if I just write that? With respect to x, which means we just want to do dx on both sides of the equation. So let's do that. So I'm going to take this equation, I'm going to copy it here. This is part A. Take this equation, we're trying to find dy dx. So I take the derivative with respect to x on the left side of the equation. And then I will do the same thing. I will take the derivative with respect to x on the right side of the equation. By the way, I just posted the grades this morning for the quiz, the one that we did at the beginning of class last time. And there was one person whose screen name was like Mr. Guest or something like that. I have no idea who that is. And then if somebody, if somebody sent me their answers in the chat for some reason, I can't find the chat dialogue. Normally it saves it to a folder and I can't find it. I'm going to look a little more for it. I'm not sure where it is. Was there anyone who did the chat, responded in the chat on the quiz last time? No? Okay. All right. So if you were whoever that Mr. Guest was or whatever, please send me an email because I don't know who you are and you probably got a 0 on it. Okay, so take the derivative with respect to x. So what do we think here? Shall we call on people? Let's call on people today. That sounds like fun. Oh. Landon, are you there?
Yes, sir, I'm here.
Okay, how do you feel about taking the derivative with respect to x on the left-hand side? All I heard was, Does that mean you're not sure?
Yes, sir, I'm not sure.
Okay, well, make sure you got about 48 hours to figure it out, right?
Yes, sir.
Okay. Valerie,
Yes, sir.
how do you feel?
Yeah, I'm getting there.
Okay, so what is the derivative of x squared with respect to x?
The x squared
Yeah, what's the derivative of it with respect to x?
is
Oh, are you unsure?
nah,
Not sure?
yeah, I'm not sure.
Okay. All right, Matthew? Is Matthew here? No? How about Roberto?
Yeah, so if I'm not mistaken,
Okay.
first we would get the x squared would just turn into 2x.
Okay, good.
And then we would do plus, and then we would do dy over dx. But would
Okay.
it be my question was because I was looking through my notes and I don't recall. Would it be dy squared over dx or just dy dx?
It would be, well, neither. It would be, you have to look at this y squared since the variable.
Oh, I
y
recall.
is
Okay,
not a-
so
okay,
yes,
go ahead.
it's 2 times dy over dx, right?
Close to, there is a dy dx, but it's not 2 dy dx, it's 2y.
Y. Yes. Okay.
So it's chain rule, right? You have the blue thing squared. What's
That's
the
what it
derivative of
was.
the blue thing squared? Well, it's 2 times the blue thing, right?
Y. Yes.
And then you do chain rule and say, okay, now I need the derivative of y with respect to x, which is dy dx.
Yes. Okay. Yes. Yes. Okay. I got it.
Okay. So that completes the derivative of the left side. Equals, okay, let's keep going here. Jose,
Yes, sir.
how about the right side? How do you feel about that?
Let's see. So I believe, so I think
What are you
the
gonna
x
have to
goes
do
away,
to this?
the x goes away, right? Whenever you, or wait, oh no, that's a multiplication.
Yeah,
That's a
you got
product rule.
product here.
Yeah.
So do your product rule, right? Which is, what is the derivative of the first one?
Which would be 1,
1, okay,
and then
times the second, right?
y
Plus,
plus derivative of y, which would be dy dx,
yes, dy dx, and
and
then,
then times x.
good, perfect, that's it. So that's the product rule being run on this first part. That is the complete product rule here, good. Plus, I think you can get the rest,
Plus
Jose.
1,
Plus 1,
and then plus dy dx.
dy dx, there it is. That's it. That is our derivative. That is what happens when we take the derivative with respect to x on both sides of the equation. We get 2x, let me just kind of clean it up, plus 2y dy dx equals 1 times y is y, plus dy dx times x plus 1 plus dy dx. So now that I've got the derivative, I need to solve for dy dx. So I need to get all the dy dx's on one side of the equation. So that means that, let's move everything to the left. This will stay on the left side. These two terms are attached with multiplication. So those two are going to have to move over to the other side. And this guy's by itself needs to move over to the other side. On the other side of the equation, I have a 2x that needs to move to the right side. And that's the only thing that needs to move on the left side. So my next line should be the 2y dy dx. That was this one. I'm bringing this one over. So when it has a plus in front of it, so when I bring it to the other side, it becomes minus dy dx times x. And then I'm bringing this one over and it has a plus, so I'm going to subtract dy dx. And then equals, and on the right side, I had a y and I had a 1. So y plus 1. And then I brought the 2x to the right side, which makes it negative 2x. Any questions? We're okay? Why did we do that
So
again?
pretty much we can say that we should like take the derivative as usual, but just don't forget to add the dy dx. Like,
Yes, if you'd like, you can think of it that way. That's fine. Right?
okay.
Take the derivative, like when you're doing derivative y squared, just do it as usual, 2y, but just remember you're gonna have a dy dx there. And then be careful because when you take the derivative of y by itself, it's not 1, right? It's just dy dx. Right, okay.
Professor,
Yes,
I had a question real quick. For the 2y dy dx, do we just look at that as one term? So when
Right
we're
here?
moving it to the left? Yeah,
yeah, this right here is one term, correct.
okay.
There, I
Thank you.
didn't move it. I left it, I just left it on the left side, which is why it's right here, yeah.
Okay, thank you.
Mhm.
I had a question.
Yes,
So if it was, if the derivative was with respect of y, so x would be dx over dy instead?
yeah, so we're gonna do that for part B. See, for part B, I'm asking you what's dx dy.
Okay.
Okay, so we're gonna do that. Good question. Just hang tight. We'll do it on the next one.
I had a question.
Yes,
Oh, sorry. Would it
No.
be wrong to put the parentheses with that dy dx with that x along with the dy dx with that 2y?
it wouldn't be wrong if you wanted to put this in parentheses like that and like that. The thing is, they're not
Yes.
necessary because there's multiplication between them. You know, like there's a multiply here. So because there's multiplication, you don't need a parentheses unless there was 2 terms and we had to distribute, but there's no plus or minus. So we don't have to distribute anything. So it's not necessary.
Got it. Thank you.
Mhm. So now that I have all my dy dx's on one side and everything that doesn't have dy dx on the other side, I'm going to factor, right? That was the whole point of this, was to now factor out a dy dx from all of the terms on the left. So I pull this dy dx out, I'm left with 2y. I pull the dy dx out of here, I have minus x. I pull the dy dx out of here, and what do I have? Minus what?
Minus 1.
1. Don't forget the 1, right? There is a 1 because you pulled that out. Then equals the other side. And then your final step is to divide both sides by everything in parentheses, because that will get rid of it on the left side and it will get the dy dx isolated by itself. Actually, don't really need parentheses here because the long division bar implies that they're separated, but it goes away here and you get dy dx equals y plus 1 minus 2x over 2y minus x minus 1. And don't start doing this. Don't start doing things like, oh, I'm going to cancel the y. You can't do that, right? Everything is separated by addition and subtraction, so you can't do that algebra there. That's wrong. So that's it. That's our derivative of y with respect to x. So let's not lose sight of what this means. It means whatever this curve looks like, okay? And remember, these curves, these implicit curves, they don't have to be functions, right? They can fail the vertical line test now. This says that if I want to know, if I want to go to some place, some point on this graph, let's say here, and I want to know the slope of the tangent line, then what I need to do is just figure out what this x and y coordinate are. Once I know that x and y, I can plug it into here, and that will generate the slope of that tangent line right there. Right? That's what that's saying. Okay, that's part A. Let's look at part B. In part B, we want to know, or I would like to know, what is dx dy? So let's do that on a different page. So here's the equation. And I want us to find dx, dy. So when I'm looking at this, right, if I want to find this, then I look at the denominator here, dy. That is what I will differentiate with respect to this time. So I'm going to take the derivative with respect to y on the left side. And then I'm going to take the derivative with respect to y on the right side. Okay. So now this will really test whether or not you understand this implicit or not. So let me ask, let's see, James, you there?
Yes,
James?
sir.
Okay, so if we want to do the derivative with respect to y this time, right? Not x, but with respect to y of these two, we can do them separately because there's addition. James,
Yeah.
what is the derivative of x squared with respect to y?
It would be 2x dx over dy.
2x, good. So that's the chain rule. The 2 comes out, we get x to the first power. And now what James is doing is taking the derivative of x, right, with respect to y. And that's not 1 anymore. That's the derivative. I'll do it in green. That is the derivative of x with respect to y, which is not 1, right? It's just something. It's actually what we're looking for. So we're glad to see it, right? It appeared.
Mhm.
You want to keep going?
And then plus 2y.
Just 2y, right? Just 2y. Now, there is really, James is actually still doing the same thing, bringing the 2 out, doing y to the first power. But then when James is doing the derivative of y, it's with respect to y, right? So it's dy dy, which is 1. So we just leave it as 2y. Is that clear to everyone? In this case, when you take the derivative of x, you get dx dy, and when you take derivative of y, you get 1. It all depends on what you're differentiating with respect to, and that is dictated by what's down here. Let's keep going. Equals. Good job, James. Hele, are you there?
Yes.
Okay, are you understanding?
I'm honestly a little lost with like the dx and dy. Well, yeah, I'm pretty lost.
Okay, well, let's just try this together. Right here, we have take derivative of the right side. Let's do these two. What would the derivative of x be, Hele, with
1.
respect to y?
Oh, with respect to y.
So what I'm really asking is, what is the derivative with respect to y of x, right? That's what I'm asking. Pop the x up here, and you just get dx dy, right?
Oh, right.
Right, and then remember, that's what we're looking for. So I mean, it's okay that it's showing up because that's what we're trying to solve for. So this should just be dx dy, but then plus, all right, Hele, same thing. What is the derivative of y?
Would y be 1?
That would be 1. The derivative of y with respect to y is 1. Remember I told you all that story about me out at that club meeting that girl, right? Asked her what the derivative of x was. She said, with respect to what variable? Because it matters, right? The derivative of x right here with respect to y is not 1. The derivative of x with respect to x would be 1. The derivative of y with respect to y is 1. Okay, so this highlighted yellow part, that is like super important for us because it dictates what's going to turn out to be like a 1 and what's not going to be a 1. Okay, good. How about Nicholas or Nico?
Yes.
I saved the product rule for you right here, that x times y, we have a product rule. So what would the derivative of this be with respect to y?
Would be, it would be like the same as the other one, but the difference would be For the last one was y plus dy over dx. This one would be x
But,
plus
the derivative of this first one is what? We're doing product rule. So the derivative of x is what?
would be dx over dy.
Good, okay. Now times the second one, which is
Would be y.
y. And then now we're doing product rule plus, I'm gonna need a little more room.
X
Plus,
would be plus
now take the derivative of y with
With the
respect to y. 1 times, finish the product rule,
times x
times x. And then we have the plus sign. There we go. Do y'all have questions? Algebraically, I can take these dx dys and try and get them on one side and everything that doesn't have dx dy to the other side. I'm going to do that right now. I have the 2x dx dy. I'm bringing over from the other side a dx dy times y, and I'm bringing over a dx dy that was by itself. On the right-hand side, I have a 1 times x, I have a 1, and I bring in the 2y from the other side. So in other words, everything in red wound up on the right side. Everything else, right, let's say everything here in gray got placed on the left side. So some of the signs changed. And then
So sound like
what? Sorry?
I was gonna ask in the exam, are you gonna ask for the raw? Mean the first one, or do we have to like put the terms in one side?
If I
Okay.
ask you to
Uh-huh.
find dy dx or something, or dx dy, then you're going to algebraically have to solve
Okay.
for it. Yeah,
Thank you.
which is what I'm doing here. Is it red? Was that your question?
No, it was what if you did it opposite and so you moved the terms over to like the other side? Would it change the signs in the final answer?
It would look a little different, but it would be the same answer. So like, let me finish this one and then I'll do it the other way and I'll show you that they're the same. Okay.
Okay.
Okay. So right now I would pull a dx dy out of the left side. That would leave me with 2x minus y minus 1, right? If I pull dx dy from all three of those, the other side would be x plus 1 minus 2y. And then I divide through by 2x minus y minus 1. I do that here, 2x minus y minus 1. It cancels. I get dx dy equals x plus 1 minus 2y over 2x minus y minus 1. That would be my answer. That clear, everybody? Now, the question that Red was asking was, if we took this, I decided to move all my dx dys to the left. Red was saying, what if I did it the other way and I moved all my dx dys to the right? So that means everything in gray is going to go to the right side and everything that's in red goes to the left. So it would look like this now. On the left side, we have 2y, we'd have minus x, right? And then we'd have minus 1 on the left side. And on the right side, we would have the dx dy times y. We would have the dx dy that was by itself. And then we're going to have to bring that 2x dx dy to the right side, so that makes it negative. Factor out dx dy from the right, we get y plus 1 minus 2x equals 2y minus x minus 1, and then divide both sides by the thing in parentheses on the right. So divide through by that and it would cancel. You get dx dy. I know I'm moving fast here. Is this. Now, I know that these don't look exactly the same, but I can convince you, I think that they are. Because if I were to take on the top one, what would happen if I took the top one and I factored a -1 out? If I did -1 here, I would get -2y plus x plus 1, right? And on the bottom, if I factored a -1 out, I would get a -y minus 1 plus 2x. And this -1 over -1 becomes +1. So these basically cancel each other out. And what you would have is this thing in red, which matches that numerator, and this thing right here, which matches that denominator. In other words, they are exactly the same. It's just both the numerator and denominator are off by a sign, but the combination of them both being off by a sign is really like you multiplied by 1, which is weird, but it's the same answer. Red, you satisfied with that?
Yeah, it happened on the homework and I was looking and I was like, oh, all my signs are flipped. What happened?
That's okay. As long as they're exactly flipped in both the top and bottom, you're fine. Okay. So we proceed. Part C. Now I want dy dt. This is new. Okay, we have not done one of these. I want dy dt. What the heck? Dy dt. How are we going to find dy dt? Because dt, my equation doesn't have t in it, right? My equation doesn't have dt in it, or sorry, doesn't have a t in it. So think about what I just said. Our equation has x's and y's, right? We're differentiating with respect to another variable t that does not appear. So when we do dy dx, right? When we do something like the derivative with respect to x of y, this turns into dy dx. If I do the derivative with respect to y of x, this turns into dx dy. The only time I get a 1 is if I'm doing something like this, derivative of x with respect to x, then I get dx dx, which is 1. Or if I did the derivative with respect to y of y, then I would get 1. Sorry, I would get 1 as well, right? So the only time you're ever getting 1 is if the variable you're differentiating with respect to is also one of the variables in the equation, right? If I differentiate x with respect to x, I get 1. Y with respect to y, I get 1. But if these variables are different, you do not get 1, right? So if I'm going to differentiate this with respect to t on both sides of the equation, do you all understand? I'm never going to get 1s. Nothing is ever going to be a 1, ever. Let's see. If I go derivative with respect to t on the left, and then the derivative with respect to t on the right, right now, I just want to kind of let you know, right now what we're doing is we're establishing the mechanics of taking these derivatives. When we do the next section, which is called related rates, you'll see why we need this, okay? So right now, you don't really know what we're going to do with this, just we're trying to get the mechanical process down, all right? So what do you think here? Duck, you ready?
Yes.
Okay, so tell me what you think. If I ask you to take derivative of x squared with respect to t, what would you say?
2x plus times dx over dt.
There you go, dx dt. So Duck was using the chain rule, right? First, what was the derivative of x squared? Well, you have to bring the 2 down, 2x to the first power. Then what's the derivative of the actual x? With respect to t, that's not 1, that's dx dt. Perfect. You want to keep going, Duck? Plus?
Yes. Plus 2y times dy dt.
Good. Again, the same thing, right? The 2 on the y comes down. Okay, y to the first power, and then having to take the derivative of y this time with respect to t, again, dy dt, that's not 1, it's dy dt. equals. Good job, Doug. Let's move on. Let's see. Ash, you there?
Yes, sir.
How you doing, Ash?
Just a little sneezy, but I'm fine.
You want to do the x times y, the product rule here?
Yes, yes, sir.
Okay, go ahead.
It would be dx over dt
Good,
times y
good.
dy plus dy over dt times
Okay.
x.
Perfect. Okay, everyone follow that? Ash did the derivative of x with respect to t, which is dx dt, times y. So doing the product rule here, right? Derivative of the first one times the second, that's this. Plus, continue the product rule. Derivative of the second one. Well, the derivative of y with respect to t is actually dy dt, right? It's not 1. And then times the first function. And then the rest of it, I'll just do myself. The derivative of x with respect to t is dx dt. And then plus the derivative of y with respect to t is dy dt. Wow, that looks messy, doesn't it? But that's the answer. That is the derivative, okay, with respect to t. Now, what are we solving for? We're trying to figure out what dy dt is, right? Dy dt. Let's look for dy dt's. I've got one here. I've got one here. And I've got one there, right? Everything else is a dx dt. So what I'm going to do now is everything that has a dy dt in it. So all these red ones, let's get those all to the left. Everything that does not have a dy dt, let's move those to the right. Okay. So now we're kind of playing that same game. I'm going to have 2y dy dt minus dy dt times x. That was this one, moved over, and then minus dy dt. That was this one, moved over, now it's negative. Equals, let's see, on the right-hand side, I have all the green ones. So dx dt times y, that's this one. Then I have this dx dt. And then, let me see, I had to move the other one on this other side. I had to move that over, so it becomes minus 2x dx dt. Ooh, okay. All these have dy dt, so I will factor it, right? I will factor it out. So I have a dy dt. I have 2y minus x minus 1. On the right side, I'm just going to leave it alone, dx dt times y plus dx dt minus 2x dx dt. And same story we did before, I'm going to divide both sides by that 2y minus x minus 1. So I'm going to cheat here. I'm going to copy this, paste it here. I'm taking that entire thing and dividing it by 2y minus x minus 1. Okay. That's our answer. And there's something extremely different about this answer compared to everything we've done up to this point. Okay, this is very different than anything we've done. All right, and I want you to see it by going back and looking at the previous answers. When we did the first one, right, dy dx, look at what our answer was. Dy dx, let me copy this here. Okay, let me put it over here. This was dy dx. Then when we did the next one, which was dx dy, we got this answer. Okay. And what I want you to see is that in order for us to determine, right, in order for us to know what dy dx was, the rate that y changes with respect to x, the only thing you have to provide me in order for me to tell you that slope of that tangent line all you have to be able to tell me is what X and Y are, right? Give me X and Y and I'm in business, right? Give me the X, give me the Y. I will tell you the rate at which Y changes with respect to X. Same with dx dy. If I want to know the rate that X changes with respect to Y, again, just give me X and Y, right? I'll just plug them in and I'll be able to tell you that, right? This one is different. In order for me to tell you the rate at which Y changes with respect to T, not only do I have to tell you what X and Y are, right? Not only do you need X and Y, right? You need X and Y to determine that. What else do you need?
T?
You need this, right? You also need dx dt. This is fundamentally different. I'm going to say it again because it's so important. Over here, in order to know the rate at which Y changes with respect to X, all I needed was a point on the graph, right? An X and a Y coordinate, I'm in business. To figure out the change in X with respect to Y, I just need a point, X and Y. But if I want to know the rate at which Y is changing with respect to T, not only do I need to know a point on the graph, I also need you to tell me the rate at which X is changing with respect to T. Then I can tell you how fast Y is changing with respect to T. All right. So there's a lot more information that I need in order to be able to answer this question, which is what I'm leading you into the next section. Okay. Because these word problems, you'll see. All right. Let's see. Should we look at the last one here? What was the last one here? I wanted dx dt. Oops. Oh, you know what? I'll just copy this. So for the last one here, I want to take this and I want to find dx dt, right? That's what I want. And I notice again that the variable t does not appear here, does it? Doesn't appear at all. So I'm going to have to take the derivative with respect to t on both sides of the equation, aren't I? Nothing's going to turn into a 1. Nothing at all, right? Nothing at all. Well, isn't that exactly what we just did in the previous work? Isn't that exactly what we just did? Didn't we just take this and do the derivative with respect to t on both sides? Right? So we should have the exact same derivative. The only difference is instead of solving for the blues, I would want to go and solve for the yellows. Do you see the dx dt's in there? So you get all your dx dt's on one side, everything else on the other, factor, divide through, get an answer. Make sense? I'm not going to do that one. It's because it's the same derivative, just solving for something different. All right. I think we're ready. I think we're ready. Let's see. Let's see, I'm trying to figure out what order I want to do this. Am I ready to get into this? Yeah, I'll wait on that. Okay. All right, so before I begin this section, related rates, okay, before I do this, I want to remind you that in your formula sheets in Canvas under files, you have a sheet here. It's called the related rates worksheet. Okay, it's in Canvas. This worksheet, I allow you to print this, and you can print it out and use it on your exam. All this is a kind of a summary worksheet that helps you work through the word problems for the section we're about to do. All right. I think it's useful. You'll see how I use it as I work through some problems. All right. So just be aware that it's there. When I bring it up, you'll know what I'm talking about. All right. Related rates. Let's go. So we are in the last section of this chapter on derivatives, related rates. There's a lot of words here. So basically what I say in this paragraph is now you know how to take derivatives, you know how to use implicit differentiation. It's time to do some word problems. This is not going to be fun because no one likes word problems, but there is a kind of a systematic approach to these. And the more you do, the better you're going to get with it, the more comfortable. But there is an expectation that you have the knowledge that you know basic geometry, trigonometry, formulas for areas and volumes. Like everyone in here should know what the area of a triangle is, like what the formula is. Everyone here should know what the area of a circle is. And for things that you may not know, you need to know that your formula sheets do have some of your basic formulas. So right here, the very first reference page of your formula sheets has a triangle, circle, an area of a sector of a circle. It gives you formulas for area, circumference. For a sphere, that's three-dimensional. They give you volume and area. For a cylinder, volume. For a cone, volume. You just need to know that all these are here because we're going to need them. All right. Along with, you know, other things like the area of a rectangle, like basic stuff you should know. So, you all ready? Ready for this? We will begin slowly and work our way into more difficult problems. So we're going to start with like 2 + 2. All right, is like what we're starting with here. Excuse me, hold on. All right, so there is a procedure that you can follow for related rates. I'm going to come back to this, okay? I'd like to work through an example first. I think it's better if I do an example to begin with. After I do the example, then come back and kind of show you what I was doing, all right? So we're going to start off with I just want us to focus all of our attention on a circle, all right? So I'm going to copy this real quick. And let's go to our notes and let's talk about this. I'm just talking about a circle right now, right? This could be any geometric shape, but we're just going to start baby steps, circle. All right, so let's get some preliminary things out of the way. First question, if the radius of a circle is 3 feet, then what's the area? So to do number one, I'm giving you that we have a circle and the radius is 3 feet. And I'm asking you for the area, right? So everyone in here should be comfortable with the idea that the area of a circle is pi times the radius squared. That's a formula you should know. So the area of a circle with radius 3 would be pi times 3 squared, which is 9 pi. And that would be square feet because we're measuring an area. And anytime you're measuring area, the unit that you're measuring in will be squared. You could turn pi into a decimal and get an approximate answer on your calculator, but I'm just going to leave it as an exact answer, 9 pi. Everyone comfortable with that? Yeah. Look at the second one. For the second one, I'm giving you that the diameter of a circle is 2.5 feet. The diameter of a circle is 2.5 feet. And I want to know what its area is. So I want to know the area. Well, again, we know that the area is pi times the radius squared. The problem with this formula is that the area of a circle is connected to the radius of the circle. And we are given information about the diameter, right? So you need to understand what the diameter is and how it's related to the radius. So what is the diameter? What is the relationship between diameter and radius?
Is to radio?
It's twice the radius, right? So knowing that, what would the radius of the circle be?
1.25.
Yeah, just half of that, 1.25 feet, right? So that's just using the knowledge that we know the diameter is twice the radius. So we could divide both sides by 2, and we know that the radius is half the diameter. Once we have that, we can now use this formula, pi times 1.25 squared. We get our calculators out. I'm going to go ahead and do the whole approximate decimal here. So we should get here 1.5, whoa, yeah, 1.5625 times pi is what my answer is. But then I'm going to approximate that, oops, times pi. What the hell's my pi key? It's approximately 4.91 square feet. We good? Look at the third one. Let me put this one over here. For the third one, if the diameter of a circle is 1 foot, what's the circumference? So the diameter of a circle is 1 foot. I'm asking for the circumference. So you need to know what the circumference of a circle is. Does anyone know what the circumference of a circle is?
2 pi r?
2 pi r. 2 pi r. So it'd be useful if we knew the radius of this thing, right? But I've given you what, the diameter? So what's the radius?
0.5?
Half of it, right? Half, or I say 0.5. I'm going to do a half a foot, right? Which means that my circumference now is 2 pi times a half, because that's the radius. And I could put the half and the 2 together, they would cancel out and I would just get pi, wouldn't I? Pi. And my units here would be feet, because circumference is a measurement of the outside of the circle. Still good? Fourth one. I'm gonna move, I gotta copy these because I'm out of room here. So for the fourth one, it says, if the circumference of a circle is 100 inches, what's the area? Ooh, wait, what? Okay, so I'm given here, the circumference of a circle is 100 inches. And I want to know what the area is. But wait a minute, area is going to be pi r squared, right? Which means we need to know what the radius is. Do I know what the radius is right away? No, right? Because I'm given the circumference. But circumference is 2 pi times the radius, right? That's the formula for the circumference. And I'm saying that that's equal to 100. So if I replace the circumference with 2 pi r and set it equal to 100, can't I solve this for r? I can just divide both sides by 2 pi, which means my radius is 50 over pi. And then what I can do is I can replace that into this formula. And my area will be pi times the radius, which we just said was 50 over pi squared, which is pi times, let's see, 50 squared, what's that? 2,500 over square the pi squared. And then cancel one of the pi's, right? This pi cancels with one of those. And so your answer should just be 2,500 over pi. And this is a measurement of area. And what were we measuring in inches here? So this would be inches squared. 25 over pi square inches. Questions? I know it's probably been a long time since you've done anything like this, but would y'all agree there's really nothing that I'm doing that has any calculus right now. It's just solving for something, right? The fifth one. Okay, I give you that the area of a circle is 24 pi. And I want to know what the circumference of that circle is. Well, circumference we know is 2 pi r, right? That was the formula for circumference, which means I need to know the radius. And here I don't have the radius, but I know that area is pi r squared, and that must be equal to 24 pi, right? And I can divide both sides by pi and get that. And then I could take the square root on both sides and get r is equal to plus or minus the square root of 24. And I will throw away the negative answer because my radius needs to be positive, right? A circle can't have a negative radius. So I have positive root 24. And that I can plug into this to get my circumference is 2 pi times the square root of 24. That was my radius. So I'll just leave it like that. That's fine. And this will be what, I didn't give a unit, did I? The area is 24 pi. I didn't give like inches or feet or anything, so I can't give an answer, a unit for this. I can just give a numerical value for it. Do you understand what I'm doing here? Are there any questions? Y'all are good?
I have
Okay.
a question.
Yes.
Why didn't turn positive? I didn't understand that part.
Why is it only positive here?
Yeah.
Not the negative? Is that what you're asking?
Yes.
Because r is the radius of a circle, right?
Yeah.
So we would not have a negative radius. Or else
Oh.
it wouldn't make sense, right? So within, this is a good question because look, if this was your entire world, what's in blue? If I just walked into class today and I asked everyone, hey, solve this equation, r squared equals 24. You have two solutions, positive or negative square root of 24. But within the context of the problem, the radius has meaning, right? The r has meaning. It's the radius of a circle. And therefore, we want to throw away the negative because it wouldn't make sense to have a negative radius.
Yes.
Okay. All right. Everyone said they're okay. All right. Read this. In all of the problems that we just solved, our circle is in a static state, meaning that if I tell you the radius of a circle is 3, that means that circle has a radius of 3 and that's it. It's not bigger, smaller, or changing. It's just 3. If I say the diameter is 2.5, then that's it. That is a fixed circle, right? Everything is static, not moving. Not moving. That's what I mean by static. So in all of the problems that we've done, everything's in a static state, right? In all the questions above, you needed to simply find an equation relating the thing that you know and the thing that you don't know, right? You somehow related them together and then just solved for the unknown. That's all we've been doing. This is just algebra, right? In this section, we are not interested in the static state of things. We don't care about static state. Static state's easy, okay? Instead, we will be asking questions about the instantaneous rates of change. More specifically, the way the rate of change of one variable affects the rate of change of another. So instead of having a static circle, we're going to have a circle that's growing. And we're going to be asking about how fast certain things are changing at certain points in time. So we're going to introduce a new variable into this, and that is time. All right. So instead of having a circle just sitting there, okay, we're going to have a circle that's somehow changing over time. And we're going to be asking at a specific point in time, how fast is something changing? That's what the whole idea of this section is. It's called related rates, because what we're trying to do is see if we can somehow relate the rate that one thing changes to something else, right? So a small change in one thing, how does that have an impact on other things that are changing? So we are going to start all of this with a basic circle, expanding circle problem, all right? So I have an animation here, all right? This animation, what's happening here is I'm going to start drawing a circle, and I'm going to draw it in a way that the radius grows at a constant rate. Okay, so I'm going to press play here. Here we go. There's a circle that is growing. Okay. And I've programmed this so that the radius grows at a specific rate. Let me speed it up just a little bit. There we go. Okay. So it's growing, the circle's growing and growing and growing and growing and growing and growing, right? So I want you to pay attention to something right now. I'm going to continue this, but I want you to kind of count in your mind, and I want you to keep your eye on the edge point of the circle along the x-axis. Okay. I want you to just watch the edge of that circle along the x-axis. And if you think of it as a point, notice how it's just moving at a constant rate across the x-axis. It's not speeding up, it's not slowing down. That's the radius, right? That's the radius from the center to that edge point. Watch the point, notice it's just constantly moving. Okay. I'll see it, you see it tracking along here. That is moving at a constant, nice, smooth, constant rate. Do you all agree? It's not getting faster or slower. The radius is not getting faster or slower, just moving along at a certain rate. Okay, y'all understand that? Let me back things up. Let me go to when the radius was 1. Here's the radius at 1, close to 1. There, close to 1. Look at the area of the circle right now. Okay, when the radius is 1, the area is about 3.23. Okay. Now I'm going to let it grow by 1. Okay, so now instead of being at 1, I'm going to move it to 2, about 2. Okay, so now the radius is 2. And what's the area? Well, 12.62. So how much did it grow by? The radius grew by a foot, right? 1 foot, or let's say 1. The radius grew by 1, went from 1 to 2. The area grew by about how much, approximately?
9.
9 or so, okay, about 9. What's going to happen when I go from 2 to 3? Do you think that the radius is going to grow by 1? Do you think that the area is going to grow by 9 again? Let's see.
No.
Let's see. I'm going to grow it to 3 now. Okay, so that's about 3. So you can see here that the area has now grown to almost 30, right? I'm going to put 30 here. So how much did it go up by? Like 17 almost, right? About 17. See, here the change is the same. The radius is changing by the same amount, 1, 1, 1, but the area is not changing at the same rate. Do you all agree? Let me keep going. If I go from 3 to 4, okay? So when I go to 3 to 4, it changes by 1. The radius changed by 1, but the area has now gone to like what, 51? So now that's gone up by what, 21? That makes sense or no? This rate on the left-hand side, this rate is constant. But this rate is not constant. It's almost like if you were to kind of draw it, like here was the circle of radius 1, right? And we had a certain area. But when you go to the next layer and you go out to 2, you've added all of this, right? That all got added. And then when you go out another layer to 3, now you've added even more. And every time you go out another layer, because you're further away from the origin, you're adding more area each time. Is this clear to you? So the question that we ask in calculus is this. Let me animate this for you again. We have this circle that's growing where the radius is growing at a constant rate. And here's the calculus question. You ready? Here it is. Right, I'm just going to make up a point in time. Right now, okay, when I said now, I want to know how fast the area was changing. Okay, right now, how fast was it growing? How fast was the area changing? All right, that's the calculus question. I want to know at an instant in time, any instant I want to know how quickly that area was increasing. We know it's not constant, right? We know it's not constant. So, and we also know it depends on what size the circle is. If the circle is really small, like right here, I could say right there, how fast was the area increasing? That would be a different answer than if I asked you right now, how fast is the area increasing? Do you see that it would be different depending on where I ask you? Because the size of the circle is different. So that's the calculus question. How are we going to do that, right? That seems like a very troubling problem to ask. So here we go. This is the calculus question right here. This is it. This is the way you would see an example. This is the way you see a problem on a test. If the radius of a circle is increasing at a constant rate of 0.5 feet every second, then how fast is its area increasing when the radius is exactly 4 feet? Okay, so we have this circle. I'll put the problem back up. This circle is increasing. I actually have it set up right now, exactly that. It is growing by half a foot every second. And I want to know exactly when we get to 4, right there, right at 4, at that instant, I want to know how fast the area was growing. Let's go do it. Take a drink. All right. So let's wrap our heads around a few things in here. The radius of a circle is increasing at a constant rate of 0.5 feet per second. Everything in yellow is information that they're giving to us, right? They're giving us that information. This is telling us how fast what is increasing? The what?
The radius.
Yeah, they're giving us information about how fast the radius is increasing, right? The rate that it's increasing. And they're telling us that it's 0.5 feet per second. They're saying to us, the radius is increasing at a rate of 0.5 feet per second. That is a speed, right? 0.5 feet per second is a speed of something, how fast something is changing. Do you all agree? Like when you look at your speedometer, 25 miles per hour, it's a distance divided by time, a length divided by time, feet divided by seconds. That's a speed. Speed is a derivative. Remember, position, if you have a position function, the first derivative is speed, isn't it? First derivative is speed. So in some way, they're giving us a derivative right there. They're telling us in that yellow and green and blue, they're telling us right there that the rate at which something changes with respect to something is 0.5 feet every second. Can somebody tell me the rate, the rate at which what's changing with respect to what here? They're giving us the rate at which what's changing?
The area with respect to
Not the area. They're not telling us
Your radius?
the radius, right? They're saying, look, the radius of the circle is increasing at this rate. So they're giving us the change in R, right? They're giving us the change in the radius with respect to what?
Time.
Time. Time. So I'm going to call it T. So they are giving us, this is the change in the radius with respect to time, right? The change in R with respect to T. Do you see why we just did problems with D something dt, dy dt, dx dt? It's because in this word problem, they're telling us the rate at which the radius is changing with respect to time, right? That's what they're giving to us. This information is given to us, right? And then look at the next part. Then the question, how fast is the area increasing? Chill out, dude. How fast is the area increasing? Well, what is that? How fast? Fast. Fast is what? Fast is a measurement of speed, right? Speed. They want to know the speed of the area, right? The speed of the area. How could I write that as a derivative? They want what? D something over
First.
D something. What? Say again?
It's gonna be the first one of dr/dt. The first
Well,
derivative.
dr/dt, we already know how fast the radius is changing, right? With respect to time, we know how fast it's changing. But we want to know how fast the what?
Area.
Area is changing. So this should be
A.
dA. Good. dA, I'll do capital A. dA with respect to time. How fast is the area changing, right? Change in area with respect to time. That is exactly what they want to know, right? How fast is the area changing with respect to time if the radius is changing with respect to time at 0.5 feet per second? And they want to know this information. They want to know at exactly this moment, right? When the radius is 5. So we want to know this at r equals 4 feet. Did I say 5? I'm sorry. Let's say 4. Okay, hold on, y'all. I gotta chill this dog out. I don't know what's going on. Okay, my apologies. I don't know if he's going to continue to be quiet. I told you all about my dog, right? Yes. No, I shared it with some people. Some of y'all know this already.
Heard about the dog yet?
Yeah, so I had two dogs. I had to put one of my dogs down last week. It was very, very tough. And they've been together for 10 years. And so the other dog is kind of like still coping. He normally doesn't bark, but it's normally because he has his friend next to him all the time. So yeah, he's acting a little weird right now. So hey, chill. You're good. Anyway, I'm going to let him stay in here. Hope you all don't mind that I'm not going to kick him out. All right, let's continue. So again, big picture here. When you read these problems, they're going to give you some rate of change of something. They're going to ask you about the rate of change of something else. And they're going to ask for it at a specific point in time. So they gave you how fast the radius was changing with respect to time. They're asking how fast the area is changing with respect to time. And they want to know that, you know, how fast that area is changing with respect to time at exactly the moment the circle had a radius of 4. Okay, that's all the information they've given to us. Now, how in the world are we going to do this, right? Well, one thing we can kind of take from what we just did in the previous exercise that we started class with is that I have a dr/dt here, right? That I'm given. And this right here, this is what I want, right? I want that, a dA/dt. And I have a dr/dt. So when you think about implicit differentiation, we know that if we differentiate with respect to t, nothing is going to turn into a 1 unless we have a t in the original equation, right? Just like we were doing in these problems, like the only way we ever get a 1 is if this variable is the same as one of these variables. So what we're going to do is we're going to be clever here. We're going to see, can we find an equation, any equation we can think of that has to do with a circle that somehow would connect the radius of the circle to its area? Well, yeah, right? I mean, we know the equation, the area of a circle is pi r squared, right? That is an equation. Do y'all agree that that is an equation? That it has 2 variables in it, area and radius. Yes? pi is a constant. Just treat the pi like it's a number. So that is an equation, right? This is a known equation. Everyone's happy with that equation, right? We're happy. That's an equation. But the key is that it has a and r in it, right? Both a and r. So what I can do now is I can just be clever and I can take the derivative with respect to t on both sides of this equation. Now, the reason I'm doing this, and I don't want this to be lost here, the reason I'm doing this is because I know that I'm gonna get a dA dt, right? I'm gonna get a dA dt when I differentiate. Because a and t are different variables, right? So when I take the derivative, I'm gonna get dA dt somewhere. And I also know because there's an r in here and I'm differentiating with respect to t that I'm gonna get a dr dt, right? And that happens to be what I'm given and what I want, right? So somehow from differentiating this equation with respect to time, I'm going to find all the things I'm looking for and all the things that I'm given are going to be within this answer. So let me differentiate that. So let's see. Sophia, you there?
I'm here.
Okay, Sophia, how do you feel about me asking you what the derivative of a with respect to t would be?
Would it be dA over dt?
Exactly what it would be. It'd be dA over dt, and that's it, right? That's it. That's the derivative of a with respect to t is dA dt, and we're done. That's the derivative of the left side. Now, on the right side, you want to keep going, Sophia?
Sure.
Okay. So we have a constant, right? Pi is a constant in front of the r squared. So the constants will come for the ride, right, Sophia?
That's right.
So I'll put pi. And now what is the derivative, Sophia, of r squared with respect to t? Do a drum roll.
Would that be the product rule with that one?
You don't need the product rule with the pi because the pi is the constant. That's what I was saying. The pi is just going to come for the ride. All you need is the derivative of r squared.
So it'd be 2r?
2r, okay. That takes care of the power comes out. You have r to the first power. Are we done or no?
And then it'd be dr over d2?
dr dt. Perfect. That's it. Everyone see that? We have the derivative with respect to t. And look, everyone, this is freaking beautiful. Look, dA dt is what we're trying to solve for, right? dr dt was given to us. And r, we know at the moment in time we're talking about. So basically, I have everything I need to fill this out. dA dt, left side of the equation, will be equal to pi times 2 times the radius. What was the radius? 4 times dr dt. What was dr dt? 0.5 or a half. I'm going to put a half here. Is that all right instead of 0.5? And that's it. dA dt is, let's see, half of 4 is 2. So 2 times 2 is 4. So 4 pi. 4 pi is the rate of change of the area at that exact moment in time. Now I need a unit on this, okay? I need a unit. So the way you figure out the unit, the way I like to figure it out is I look at first, what's area? Well, how do we measure area? Look at the problem here. Everything here is measured in feet, right? So if I'm talking about the area of a circle, I should have, what is my unit for area?
Feet squared.
Feet squared. So I'm going to put feet squared per. And then on the bottom, do y'all see I have time? And how is time measured in this problem?
Seconds.
Seconds. So per second. There you go. We just did our first related rate problem. We knew that a circle was growing with the radius growing at a certain rate. We were then asked to figure out the rate at which the area was changing. We related those rates, right? We related them together. How did we relate them? By the differentiation. The differentiation created a new equation that related the rates together, and then we just solved. And we were done. I feel like I'm more excited than you are. So this works for any equation in the world, all right? If you want to relate any rates together, all you have to be able to do is implicit differentiation. If you can do that, you can relate any two things together. I'll talk more about that later. Let's do another one. Yeah. How are y'all doing? 2:15, we still have a little time. So in the example we just did, we said that if this circle is growing, right? If this circle is growing so that its radius is increasing at a constant rate of 0.5 foot per second, then at the exact moment the circle has a radius of 4, which let me wait for it to get there again. At exactly right there, right at that moment, I can tell you that the area was increasing at 4 pi square feet per second. Come on, dude. Well, let me just take them, do something.
So Ash, did you omit?
What's up?
Did you meet for the review, or you want to meet later?
Oh, I can meet tonight.
Yeah, I can do tonight. I did like half of it, but we can like solve the rest together. And if someone wants to join, if we could.
Absolutely. What time are you thinking?
Someone wants to join?
I'll join you guys.
Okay.
Awesome. How does 7 sound? Or actually not 7, sorry, 7:30.
That works for me.
Are y'all doing a study group or something?
Yeah.
Okay. If y'all do, just reach out to me. If y'all are stuck on something, just text me, or, even if it's not my office hours, just reach out.
Oh, is it okay to text you like at 7:30 or?
Yeah, whenever. So look, I want everyone to understand that with this problem, we're trying to figure out the rate at which the area was growing at exactly that instant at 4, right? If I repose the question, I asked you what's the rate, right there, 2 seconds, like a split second later, your answer is different. It's an instantaneous rate of change. It's what's happening at an instant, not on an average, but exactly at a moment in time. All right. Okay, let's look at the next question. This will probably be our last one for today. Okay, an expanding circle, still talking about a circle. This time there's something different. Wait, oops, I didn't grab the actual question. Oops, I grabbed the wrong thing. Okay, here we go. So for this one, I say we have an expanding circle, but this time the area is increasing at a constant rate, not the radius, the area. So I'll show you a picture of that, okay? I'm going to show you, it's different than the one we just looked at. Notice when I play this one, the area is going to increase at a constant rate. The radius is not. So keep an eye on the radius and watch how it does not grow at a constant rate. Do you see it slowing down? Do you see that it's growing? And if you track that point, this edge point right here, notice that as time goes on, this is it's getting slower and slower and slower. Watch in the beginning, it's going to grow real fast and then slowing down. That's because it's almost like if you were pouring paint onto the floor and you were pouring it, out of the can at a constant rate, it would start growing fast initially. but then it would slow down because it's got to cover more space. Does that make sense to you? That is different than the previous problem, right? The previous problem, our picture was this, right? And the radius here, the radius never slowed down, never sped up, never slowed down. It was always the same pace the whole time. Two completely different problems. So let's see if we can do it. So first we start off, we say, okay, the area of a circle is increasing at a constant rate of 1/5 square feet per second. Okay, it's increasing at a rate, a rate. You should be thinking rate, derivative, derivative, derivative. So they have given to us what? What are they giving us here? The change in what over what?
A over T.
A over T, area over time, right? And they're giving that to us as 1/5 square feet per second, right? That's given to us, how fast the area is changing with respect to time. And then their question is then, how fast is the radius increasing, right? So what is it that we want? The rate at what? The rate of what?
Radius of R over T.
dr dt, right? We want to know how fast the radius is changing with respect to time. We want that at exactly what moment in time, though? At exactly the moment that what?
The area is 5 feet square.
At exactly the moment the area is 5 square feet. Okay. They give us how fast the area is changing with respect to time. They want to know how fast the radius is changing with respect to time at exactly the moment that the area is 5 square feet. Okay. Now the big part. Any questions on this setup so far? I need to connect that variable to that variable. The area of a circle to its radius. Any equation you can come up with? Same one we just used, right? The same exact one we just used. The area of a circle is pi r squared. Again, I'm using that equation because that equation has a and r in it. And that's when I'm given what I want have to do with a and r. So I better use an equation that has a and r. I differentiate this with respect to time. Isn't that the exact same derivative we just did? Right? It's the exact same problem, isn't it? In terms of the differentiation, the equation. We get dA dt equals pi times 2r times dr dt. I went through this quick because we just did that derivative, right? Notice now though, dA dt, you're given, right? 1/5. dr dt, we want, right? So I'm happy to see those. I'm happy to see those. But there's a little catch here. We need to know the radius, don't we? And am I given the radius? No, I'm given the area, right? But if I know the area of the circle at that moment in time, don't I know the radius of the circle at that moment in time? I can do what we did to start this off. Remember when I said everything is static? We can just say, oh, look, well, if this were the case, right? If this were the case, then we know area is pi r squared. That must equal 5. And if we divide by pi, we get 5 over pi. And then if we take the square root, we get square root of 5 over pi. And again, I'm not going to take the negative root because it's a radius, so I'm only taking the positive, right? So now I know what that is, don't I? So I can rewrite this equation. This becomes 1/5 equals pi times 2 times the radius, which was the square root of 5 over pi, times dr dt, which is actually what I'm trying to solve for. This, 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 right? And now to get dRdt on both sides, all I'm going to do is just divide both sides by that. And I'm done. I could use decimals. I could get my calculator out here, but I'm just going to do it this way. Take 1/5, divide everything by pi times 2 times the square root of 5 over pi. That will be dRdt. Let's get that as a decimal. Here's my calculator. So I'm going to do the whole left side on my calculator right now, and then you can check to see if you can get the same thing. Pi times 2 times I get approximately 0.025 is approximately dRdt. What are my units? What is the unit of this?
Feet.
Radius
Squared
is
over
measured
section.
in feet, right? It was feet in this problem, was it? Yeah, feet, okay. So it'll be feet here. This will be feet per, and then time was measured in seconds, so seconds. Questions? I'll go back to the picture. What we just did is we said, what did we say sorry, the radius? I need to figure out what that is. 5 divided by pi. This is about 1.26. That's what the radius is, approximately. So what we just did is we said, hey, look, this thing is growing, right? Where the area is growing at a constant rate, the radius is slowing down. But if we go back to exactly the moment when the radius was 1.26, somewhere around there. So right around there, hold on, right around there at that instant, the radius is growing at, what did we say?
0.025.
25, something like that, 0.025 feet per second at that instant. So you might be asking yourself, like, what in the world, like, how in the world would we ever need something like this, right? I mean, this seems ridiculous. I'll just give you a real quick example of this, all right? Just something, this is one of my favorite examples. And I'm gonna give you all, if I remember, I'll give you all a bonus problem on this. So let's say we have a car engine, right? And you have to know a little bit about engines here, but you have a piston that moves up and down in a cylinder. There's a gas and air mixture, spark, explosion, drives the piston down. You have a rod that connects to this circle crankshaft. And what happens is as this piston moves down, right, the explosion of gas air pushes that thing down. What it does is it moves this around and it turns this crankshaft. It turns it in, you know, starts spinning it. And then that energy gets transferred to a clutch, and then that clutch transfers it to the transmission or whatever, and then into the wheels, and then you drive down the road. So the question would be, if you know that this is moving down at a specific instant, right? You know how fast this is moving down. Maybe that's moving down at, you know, let's just say 200 inches per second. At some instant, you know how fast it's moving down. You could then ask the question, how fast is this turning at that instant? Or another way you could do it is, if this is turning, you can figure out how fast the piston is coming up at a specific instant, because the piston does not move at the same speed the whole time. Because of the circular motion of the crank, it speeds up and slows down. It's not always uniform. That's just one little example. All right, we're running out of time. I have 10 minutes. I'm not going to do any more examples. I'm going to show you the examples we're going to start to do. Okay, just want to kind of give you a preview of the problems. So here's another problem we're going to do. We're going to have, instead of a circle, we're going to have a three-dimensional sphere that's growing. And I'm going to give you some information about the rate of change of something and ask you about how something else is changing. Like if the radius of the sphere is increasing at a constant rate, how fast is its volume increasing? So it's a sphere instead of a circle. So that means we need to know about a bunch of stuff about equations for spheres. I'll give you something different. One of my favorite examples. I'll let you read it first. A plane is flying horizontally at an altitude of 2 miles and a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? So here's a picture. You have the black dot is the radar station on the ground. The red dot is the plane flying overhead. The plane is flying at a constant rate. And what I'm asking is at a specific instant in time, at a specific instant, when the distance between them is 6 miles, how fast is the distance between them changing? How fast is distance between them changing? Another question I could ask is same thing. A plane's flying overhead, but instead of asking how fast is the distance between them changing, think of it as if you were moving your head watching the plane fly over. I can ask you how fast your head is turning at a specific instant in time. Another analogy for this one is if you've ever stood like on a subway landing waiting for the subway to come or a train to go by, you can see the train way down there, you're watching it. And let's say the train just goes by, or think of like a car on a racetrack. You're watching it, here it comes, here it comes. And then if you think about your head, as the car comes, it's like you're slowly tracking them. And then the closer they get, it's like, right? Your head has to turn really fast to keep up with them when they're right in front of you. But once they go past you, your head doesn't have to turn as fast to keep up with them. Does that make sense? So I'd like to know like how fast is your head swiveling at a specific instant? That would be useful if you're trying to like shoot an airplane down, right? You have this airplane coming over and you're trying to like shoot it down, right? You're trying to track like how do you need to rotate that gun to track it properly, right? I mean, a couple of weeks ago, I wouldn't have thought that that's relevant, but it's actually pretty relevant these days, right? So these anti-aircraft guns are actually, you know, doing all this calculus, trying to figure out rates of change of things. We know how fast the plane's moving. We need to know how fast we need to turn to keep up with it, right? All these things. Here's another one. Well, let me see. This is one of my favorites. So this is like a classic calculus problem. You have a cup, okay? We're gonna start pouring liquid into this cup at a constant rate. So we start filling this with water. We're pouring it in at a constant rate. The water comes up really fast in the beginning, but because the cone spreads out, if we keep pouring in, it's gonna come up slower and slower and slower. So we'd like to know at a specific instant how fast the water level is rising. A runner running around a track. You have a runner running around a track. You have a person watching them, their coach or whatever. Why did it stop running? And then what you want to know is at a specific instant in time, if there was a rope tied to two of them, how fast is the rope being pulled away from them? Not sure why it keeps stopping, but either way. A ladder, here's a classic ladder problem. A ladder starts sliding down a wall, okay? And I don't know what's going on with my computer. It's not liking this. It's freezing up, weird. Anyway, the ladder moves, falls, and you want to know at a specific instant, if this corner of the ladder is sliding down the wall, how fast is this point moving away from the wall? There's so many different related rate problems. You release a balloon, the balloon starts to rise. Whoa, that was way too fast. Yeah, never mind. What's this one? Oh, this one's cool. You have a car, you have two like trolley cars. And then you have a wall between them and there's a pulley on top and they're connected with a wire. And this red car starts to move away from the wall and that pulls the blue car towards the wall. And the question is, like, at a specific instant in time, how fast is the blue car moving? If the red car is moving at a constant rate, how fast is the blue car moving at an instant in time? Why is there so many of those? Whoa. Oh my God. Okay, I need to fix that. All right, I think I'm done. Are there any questions? We're not going to have any homework over related rates. I don't want you to think about any of that. We won't talk about related rates till after spring break. Okay, we'll come back. I'll have to remind you of everything that we are doing, right? But at least I planted the seed in your mind in terms of what related rates are about. Focus now on the test. And that's it. We have 3 minutes. So if you have any questions, I'll hang out. If not, I will see you on Thursday. Come in, take the test.
I was just gonna ask about the quiz, because I know you said that there was someone without like their actual name, but I'm pretty sure like it was my name. But
yeah, I'm gonna look at it again, Bellum, because I know I couldn't find you and I was like, that's weird. I'm pretty sure you were here. So let me go. I'm gonna bring it up again right now and see if maybe I just didn't. Let me see. I think I have it here in files somewhere. While I'm doing this, does anyone else have a question?
I also have that question as well.
Okay, what I can do is I can show you without the responses there. Here, I can show you what I have.
because what was the strange name you had? Or
Oh, sorry. I know. Is it Mr. David? No, that wasn't it. So what I'm showing on my screen, I'm going to stop recording because I don't think this is relevant anymore. But